Hello everyone, my name is Anderson and I'm going to present the paper An Adaptive Resolution Scheme for Performance Enhancement of a Web-Based Multi-User VR Application. The work has been done by Rishabh Pathak, Anderson, which is myself, and my supervisor Gabriel Muntean. I am a postdoctoral researcher in Dublin City University, and I work as part of the Traction project, which is an European Horizon 2020 project that aims to present and develop technologies for opera. And these include virtual reality and other technologies for the delivery of opera to communities that normally don't have access to it. So in terms of virtual reality, this paper introduces optimizations that can be useful for the project. The main motivation behind it is that the performance of web-based VR applications, such as the ones built with A-frame, can be affected due to the limitations of CPU and GPU, especially in multi-user applications. Therefore, we need to understand and analyze these applications' performances under different scenarios, demonstrating how an increase in the number of users affects the metrics related to VR quality of experience. Another very important aspect is the frame rate, which is very important in VR applications to prevent motion sickness. So a choppy frame rate may affect the experience of users when they move left and right, as this is very noticeable, especially when you have the screens very close to your eyes, and then you can feel very sick if the frame rate is not stable. The multi-user VR application that we propose is an application using the A-frame library, as I mentioned previously, and it's rendered as a 360 experience within a browser. This application allows users to watch a film in a synchronized manner in a virtual cinema room, as you can see in the image there. The application employs a novel adaptive resolution scheme for VR, which is the ARS VR, that improves the application's frame rate and latency on remote devices with limited processing and display. In the applications, the users have the freedom to move, and WebRTC is used for voice chats. The A-frame also has another library, which is the networked A-frame, that allows for the broadcasts of synchronous playback to all clients, and this is also employed in the application. Here, I present the VR application architecture that uses a reverse proxy service called ngrok, and this exposes the local application server to a firewall on the public internet using secure channels. This was useful for our tests because users that are not on the same network of the server can access the application by querying the link to the secure tunnel. Also, in the architecture, we have two laptops that were used as the application server and one as a client. And the smartphone was used to simulate another client from a network that was different from the server. And this was possible due to the ngrok proxy service. So the adaptive resolution scheme for VR is presented here. The algorithm is on the right, and it starts once a connection is established, as the server starts sending the application data to the client, and the ARS VR algorithm starts. The algorithm was employed and deployed with JavaScript, and it adjusts the resolution of the application by monitoring the frame rate. The numerator and denominator of the aspect ratio are multiplied with the frame rate to provide a dynamic resolution. The application in A-frame has a default resolution of 1920 pixels for both height and width. And this is very high for certain devices such as smartphones. So the dynamic resolution is very important, especially for smartphones. But for computers, it is also useful if a computer is not performing very well, if there are other applications in the background, if you have many tabs open in the browser, as A-frame uses the browser capabilities. So the dynamic resolution is very important for improving the frame rate. And the dynamic resolution will decrease until a suitable frame rate is achieved. As I mentioned previously, a smooth frame rate is very good for users having a good experience while using virtual reality applications, as if it's unstable, it will cause motion sickness. And one of the main issues in browsers is that the frame rate will change because the browser will output a very high resolution and some frames will be lost and the latency will be very high depending on the machine and the conditions of the CPU and GPU. Therefore, the dynamic resolution will prevent that, or at least improve the situation, having a more stable frame rate for the users. The calculations that you can see in the algorithm are very important as well, because different devices have different width and height. So therefore, we need to find what's the greatest common divisor and find the ideal ratio for the screen size, as it will be adjusted. And we don't want to adjust in a way that the image looks stretched. We want it to be adjusted based on the screen ratio. The adaptive resolution scheme for VR is also the main contribution of our work, as the VR application that we built was done in order to test the approach. And the main aspect of this paper is the proposal of the adaptive resolution scheme. And this approach can also be applied to other web-based VR experiences. And they don't need to be necessarily multi-user like the one that we built for this paper. We built it as a multi-user cinema experience, so we can have more users joining to test the capabilities of the algorithm in constrained environments with more users. But it can also work in normal single user experiences as long as they are web-based VR experiences. And with the browser rendering the 3D scenarios in low resolutions, the frame rate will get closer to 60 FPS, which should be the target for a VR experience that is pleasant to users. So the closer we can get to a stable 60 FPS, the better. And that will help prevent users getting dizzy or not feeling well for moving their head left and right, checking the experiences and seeing the content being rendered. And as a stable frame rate is more pleasant to the eye, especially when you're so close to the screen. For the performance analysis, we use Google Chrome. The A-frame framework works in multiple browsers, but to get the results in a comparable manner, Google Chrome was used across all devices. The frame rate was collected for 120 seconds from the application with the algorithm off, which means that we were using the 1920 pixel resolution, and also with the algorithm on with the dynamic resolution working. The scenarios contained 4, 6, and 8 simultaneous users. And now I'm going to start presenting what we analyzed. The first item is the frame rate per second. Here I have 3 plots for 4, 6, and 8 users. On average, for 4 users, we have 36 frames per second. And with the ARS algorithm running on, this is increased to 50 frames per second with a loss resolution of 23%. With the 6 users, the average FPS without the algorithm was 29. And this is the average across the 6 users. And with the algorithm on, this was increased to 47 frames per second. So the loss was reduced in 30%. We have good results also for 8 users, and originally the average was 27 per second frames per second, and they were improved to 45. with frames per second loss reduction of 28%. I have the average resolutions there in the fourth column, but I'm going to talk about it in the next slide. So here I have the resolutions, because as we are adjusting the resolutions to improve the frame rate, one can simply say that we just go for super low resolution. Of course, the frame rate is going to be good, but that's not the case. We want to reduce the resolution to a point that it doesn't look too blurry for the users, and it's still an acceptable resolution, even though we improve the frame rate. So as you can see in the plots, there aren't many dips in the resolution to unacceptable numbers. In the beginning, it starts in a lower level when the algorithm is starting and when the ratios are being calculated. But then the algorithm gets stable and the resolutions are on average of 3 plots they're seeing. So the 4 users, we have 806 per 453 pixels. Then for 6 users, 801 by 450. And then for 8 users, 667 per 375 pixels. And I believe these are resolutions that will not affect too much the users, especially if you're in a small screen as a smartphone, which is one of the main targets of the algorithms. It's for constrained devices that don't have great capabilities for generating graphics. But even on larger screens that we tested, these are a good results. So the adaptation didn't go in a too invasive way for the users. For the latency, there are peaks of up to 800 and 700 milliseconds in cases of 4 and 6 users. They can go a bit higher for 8 users. There's a case there's 1,400 milliseconds. And that's because of the concurrency, and when new users join the session, they can reach those numbers, especially when the algorithm is not on. But the average latency without the algorithm was from 90 to 100 milliseconds, and this was improved with the algorithm from 70 to 80 milliseconds. This frame latency is related to the time that the browser receives the code that needs to be rendered on screen. So we calculate the difference by when the HTML elements are received by the browser and by the time that they are actually displayed on screen for the users. So as a conclusion, we can say that the A-frame browser-based multi-user VR application can be rendered on remote devices with limited processing and display features. The ARS VR algorithm was also introduced, aimed at improving VR performance in terms of frame rate and frame latency on such devices with dynamic adaptation of the visual's resolution. The ARS VR algorithm significantly reduces the FPS loss in the scenarios of 4, 6, and 8 simultaneous users by 23, 30, and 28% respectively. And for future work, we aim to improve the algorithm by supporting devices with different screen heights and width radios. And other applications such as video conferencing in A-frame and other device types can also be studied. Thanks a million for your attention, and I hope you enjoy the conference and the rest of the presentations today. Thank you.